All right, we're going to get started with chapter 3. Mhm. So chapter 3. Chapter 3 is platform storage, powering data at scale. All right, what does that mean? All right, what does that mean? Okay. Um, Whether you're storing images for a web application, managing a global relational database, or archiving petabytes of sensor data, Google Cloud offers powerful and scalable solutions to match your workload. This chapter will break down persistent disks, cloud storage buckets, Cloud Spanner, Cloud SQL, Bigtable. Let's get started at the infrastructure level with persistent storage for virtual machines. Persistent disks. All right, when you deploy a virtual machine in Google Cloud, one of your first decisions is about storage. Every compute engine VM needs at least one disk to host the operating system, applications, and data. Google Cloud persistent disks provide this foundational storage layer, reliable, high-performance block storage that persists independently from VM instances. The types of persistent disks. There are four main types of persistent disk options. Standard persistent disks, these are HDD. These are cost-effective spinning disk storage. Good for sequential operations of batch processing, ideal for data that doesn't require frequent access, lower IOPS, but economical for large volumes. SSD persistent disks. These solid state disk performance, higher IOPS and lower latency than standard PD, ideal for application databases and random I/O, best for production workloads that need performance. Balanced persistent disks. These are the middle ground between standard and SSD. They're a good performance to cost ratio. They're suitable for most general application needs and a great starting point for most workloads. And finally, local SSD. This is physically attached to the server hosting your VM. These are exceptionally high IOPS and lowest latency. Data loss if the instance stops or moves, so they're ephemeral. And they're perfect for high performance scratch disks or caching. For the exam, remember, local SSDs are ephemeral. They don't survive VM restarts or maintenance events. Use them only for temporary data or caching layers where data can be regenerated. Key features of persistent disks. There's powerful characteristics that make them reliable and flexible. There's transparent encryption, where all data written to persistent disks is automatically encrypted at rest using Google managed encryption keys. For additional control, you can optionally use customer managed encryption keys. Let me see. All right, there's customer managed encryption keys, CMEK, via Cloud KMS. There's customer supplied encryption keys that you provide directly. There's dynamic resizing. Unlike traditional physical disks, you can resize a persistent disk on the fly. You can increase the disk size without VM downtime. This grows from 10 gigabytes to 64 terabytes, depending on disk type. And the VM OS recognizes new space after a simple resize command. There's snapshots. Persistent disks support point-in-time snapshots. These are incremental backups and only changes since the last snapshot. You can create new disks from the snapshots. They're perfect for backup, recovery, or creating test environments. And they can be scheduled automatically. There's multi-writer mode. Some workloads need concurrent disk access from multiple VMs. This is available for SSD persistent disks. This allows read-write access from multiple VMs simultaneously. It's perfect for cluster databases or shared file systems, and requires careful application design to avoid conflicts. Performance characteristics of persistent disks, they scale with disk size. So larger disks have higher IOPS and throughput limits. VM machine types have more vCPUs, allow more disk bandwidth. And disk type. SSD outperforms standard, or HDD for random access. For example, a 500 gigabyte SSD persistent disk can deliver up to 15,000 read IOPS, 15,000 write IOPS, up to 240 megabytes per second of read throughput, and 240 megabytes of write throughput. But performance is also capped by VM size. A VM with 8 CPUs has a bandwidth cap of 4 gigabytes per second, regardless of how many disks are attached. So, when designing for performance, consider using striped disks by creating a software RAID 0 array across multiple persistent disks. This can overcome the performance limits of a single disk. Common use cases include how they excel in these areas. Boot volumes. With the boot volumes, OS and application binaries, right? Database storage. This is for reliable storage for MySQL, PostgreSQL, etc. File servers. This is backend storage for NFS or Samba services. Shared application storage when apps need a consistent file system. So, a practical example, let's say resizing a disk. Let's walk through this and give you an example. Okay. Compute. Oh, all right. Compute disks. We can create the disk. All right. We can select the disk's type. Disk source type. Well, we're not going to use a disk source. We can use the disk settings. Oh, remember, set the name, description, single zone, right? You can set the size. Okay. Set it to 100. And we can set the snapshot schedule, right? Every day. Let's see, create a schedule here. This multi-regional, we can set this daily, hourly, weekly. All right. We can set the start time and auto delete functions. And you can have a deletion rule in place. Okay. From here, you can use the Google Managed Encryption key or the Cloud KMS key that you provide. And then you can add the labels, tags that are necessary for billing, network rules, network routing. All right. And from there, you would create this and attach it to your VM instance. Well, you would want your VM instance to exist in the first place. All right. And then one command, if you wanted to resize it, let me activate the Cloud shell. Okay. And this is for Linux. Let's get this running. All right. You would do sudo resize 2fs dev SDA1. And for this would be for the Linux, right? For Windows, use the disk management utility to extend the volume. For the exam, remember, the common scenario asks what happens to a running VM's attached disk if the VM is deleted. Remember that by default, persistent disks survive the VM deletion unless the delete boot disk when instance is deleted option is selected. All right, close this. All right, cloud storage buckets, the scalable object storage. As we continue our tour of Google Cloud storage capabilities, we'll arrive at the most versatile, durable, and widely adopted option in the cloud platform, cloud storage. Backbone for storing everything from app assets to analytics archives. Think of cloud storage as your universal warehouse in the cloud. It's not limited to compute attached disks or a single server's capacity. Instead, it offers virtually infinite space that's accessible anywhere in the world at any time and by any service within or outside of your GCP environment. So let's unpack how this works and why it's a foundational piece of modern cloud architecture. So this is object-based, not block or file. Unlike persistent disks, which behave like block storage, cloud storage is object-based. Each file you upload, whether it's a JPEG, a log file, or a 2 gigabyte video, becomes an immutable object stored in a bucket. These objects are retrieved via HTTPS or the GSUtil CLI using a globally unique path like, say, GS colon slash slash, and then the name of the bucket, my photo bucket, 2025, the file folder, photos, and then the image. Let's say image 12345.jpg. Now this doesn't exist, but this will retrieve the image. Okay. All right, no folders, no file locking, just lightweight metadata, automatic integrity checking, and total scalability. So remember for the exam that cloud storage is perfect for unstructured data, backup workflows, streaming content, machine learning datasets, and static website hosting. Buckets beyond borders. Buckets are not bound to a VM or a zone. They're independent, distributed, and highly durable. You can share buckets across projects, mount them via cloud storage, fuse, serve public content like images for a website, or keep private backups accessible only to specific service accounts. And remember, each object is versioned automatically if versioning is enabled, which makes rollbacks, recovery, and auditing much easier. And let's see, storage classes. Let's try to go there. These are buckets I already have. Huh. Let's try and use that. Let's see. Oh, I already have some storage here. Configuration. Try those. This is where I can identify my project, storage account. Where? All right. So cloud storage isn't about where data lives. It's about how often you access it and what you're willing to pay for that access. There are four storage classes, each optimized for different use cases. Okay. Here's the trick. All four offer the same millisecond level latency and throughput. The difference lies in availability, durability, and cost models. Okay. So we'll name this bucket the shoes practice 2025 0401. Okay. Labels, you want to have labels, regional, multi-regions, all right, within the US, Asia Pacific, Europe, and it goes, oh, I thought it'd go down. Okay. Continue, how to store it. Okay, so this is where you're getting, we showed you the multi-regional, all right. Let's go back one, where to store it. Okay, multi-regional, data stored across multiple regions on separate continents. So we showed here the US, Asia Pacific, or Europe. This is ideal for global apps, media hosting, or user-generated content, and it delivers 99.95 availability and geo-redundancy. And it's the most expensive class because you're paying for availability and durability. Use it when speed, reach, and redundancy really matter. All right. You have regional, right? This is stored within a single region. So it's best for analytics or processing pipelines that live close to compute resources. Availability is 99.9%, but it's still highly durable. And it's slightly cheaper than multi-regional. Huh? So you can see here, Africa, Americas, Asia, and Europe, and the Middle East. Oh, that's good. Those are coming online. This is perfect when you want to reduce latency in the same zone as your data flow, data proc, or AI platform job. Right? Let's choose how you're going to store your data. Okay. Continue. Okay. You have different opportunities. Nearline. Okay. Nearline storage is meant for data you want to access less than once a month. This is available 99% with lower storage costs and 30-day storage minimum with retrieval costs. Think monthly backups, logs, or documents that must be retained but aren't active. So know that retrieval incurs costs for the exam. Don't use Nearline for regular queries. Right? For something that's active, you want to stick with standard. Next, you want to go to ColdLine. ColdLine is designed for long-term archival. You pay pennies per gigabyte to store data, but you'll pay more to read it or delete it early. There's a 90-day minimum storage term. So you use ColdLine when compliance, audit retention, or archiving large historical data sets is your goal. And finally, you have Archive. All right. Archive is the lowest cost storage for rarely accessed data. There's a 365-day minimum storage term. This is designed for data that may only be accessed once or twice per year. There's high retrieval costs, but low storage costs. This is the highest retrieval cost and the lowest storage costs. This is perfect for long-term backups, compliance archives, and disaster recovery. So for the exam, don't overlook archive storage for the PCA exam. Know that it has a 360-day minimum storage commitment and the highest access cost, but cheapest storage costs. So I repeated that. All right. And then let's see. You go to the objects. Let's talk about the lifecycle rules. Okay. One of Google's smartest features is lifecycle management. Let me see if this is here. Continue. Um, with this, you can set automatic rules that move data from multi-regional to nearline after 30 days. You can delete files after 365 days. You can archive stale backups after 90 days. This not only saves money, but also reduces manual management. For the exam, expect a scenario-based question asking when to move data between tiers or how to enforce retention policies. Okay. You see the cost calculator is over here as well. Data encryption, always important. All right. So let's see if I can go to Fuse. Mhm. All right. So cloud storage Fuse, you can mount this like a drive. Ever need to access a cloud bucket like a local directory? Meet cloud storage Fuse. Okay, this is the Fuse CLI information, but let's go over here. Okay. All right. This is a user space file system that lets your application interact with the cloud storage bucket as if it were a traditional file system. It's great for legacy apps or workloads specifying POSIX compliant path, like /mnt/logs. Just be aware, performance is lower than native object API calls, and it's not ideal for high throughput writes. Okay. You have data transfer options. What if you have terabytes of data stuck on AWS S3, Azure Blob, or even on-premises drives? Google offers tools like Transfer Service for cloud storage, where you can migrate from S3, Azure, or HTTP FTP sources. As Transfer Appliance, which is a physical hardware for shipping petabytes to Google data centers. And as Storage Transfer Service, which it automates recurring transfers from other buckets or public data sets. So note this, for 20 terabyte or more workloads, Google recommends using the transfer service with parallel jobs and bandwidth throttling. Okay. Okay. Security and IAM integration. Every object in a bucket is secured using IAM policies and Cloud KMS, the key management service. So with this, you can control access at the bucket level or object level. You can use signed URLs to grant temporary access to external users. You can enable object versioning for rollback protection. You can encrypt objects using Google Managed, Customer Managed, or Customer Supplied keys. And know that security and cloud storage follows least privilege, and audit logs are integrated into cloud audit logging by default. A couple of practice questions. Let's see. Up. All right. Next up is Cloud SQL. Okay. Cloud SQL is the platform's sweet spot for simplicity, compatibility, and ease of use. Let's go over here. Okay. Well, I think I got it over here. There we go. All right. So this is designed for developers, DBAs, and businesses who want the power of relational databases without the burden of server administration. Cloud SQL provides a fully managed environment for three of the world's most trusted open source engines: PostgreSQL, MySQL, and SQL Server. You bring your schemas and queries, and Google handles the rest. So what is Cloud SQL? Cloud SQL is a platform as a service PaaS solution for relational data. You get full SQL engine access, automatic updates and patches, integrated backups and replication, high availability and failover. performance tuning options via built-in dashboards. So for the exam, remember Cloud SQL is regional, not global. It's best for applications that don't require multi-region writes or spanner level scale. Spanner handles the global. Remember that. Cloud SQL supports multiple engine versions, including PostgreSQL. Let's see. Okay, PostgreSQL up to looks like version 17. MySQL up to version 8.4, and SQL Server up to 2022. Okay, and it depends on your subscription region. An instance can scale vertically to meet workload demand, up to 416 gigabytes of RAM, up to 64 vCPUs, and 10 terabytes of SSD back storage with automatic IF scaling. If you need more than that, you may want to consider Cloud Spanner or external partitioning strategies. With this comes built-in security. All data in Cloud SQL is encrypted at rest and in transit. Encryption is handled by default using Google Managed Keys. You also have the option to bring customer managed keys, but we have availability within Google. Connections are protected via SSL and IAM-based authentication, not just database credentials. You can even configure private IP access so your SQL instance doesn't use public networking at all. It's ideal for zero trust environments or internal applications. So when to choose Cloud SQL? It's your go-to option when you need relational data structures like tables, rows, and joins. You want SQL compatibility with your existing PostgreSQL or MySQL applications. You prefer fully managed infrastructure, so there's no manual patching or scaling, and you require regional high availability, automated backups, and failover support. For example, let's say you're building a customer-facing web application in Node.js, hosting it in App Engine, and using PostgreSQL to store orders and user info. Cloud SQL will integrate seamlessly. Also, there's high availability in backups. Cloud SQL offers high availability using regional failover. So your primary instance lives in one zone, a standby replica lives in another. In the event of failover occurs automatically with minimal downtime. Additionally, daily automated backups can be scheduled. You can also trigger on-demand backups before major schema changes. Backup retention periods are configurable depending on your needs. Monitoring and maintenance. Cloud SQL integrates with the cloud monitoring and cloud logging, so you can track CPU and memory usage, slow query logs, connection errors, and replication lag if you're using replicas. You can also configure maintenance windows, giving you control over when patching or restarts occur, so there's no unexpected surprises. You can also configure maintenance windows. Let's see. You can also configure maintenance windows, giving you full control over when patching or restarts occur with no unexpected surprising. So connecting. There are three primary ways to connect. You can do it through the Cloud Shell, Cloud SQL Proxy. The Cloud Shell is an open shell in the console. You'll see that. And use the built-in SQL proxy to connect securely. Cloud SQL Proxy is a lightweight client you can install locally or in your application container. It handles SSL and IAM authentication transparently. And you can use a public IP with SSL. So with this, you can use a secure TCP connection with whitelisted IPs and certificates, which is a good option for third-party BI tools. So for the exam, know the example between Cloud SQL Proxy, which is a secure identity-aware, versus standard IP connections, which is SSL only. The proxy is preferred when using IAM or connecting from non-GCP environments. All right. So with Cloud SQL, your bill will have a different breakdown. It'll look at instance type and vCPU count, storage volume and performance tier, that's SSD versus HDD, backups and read replicas, ingress, egress network traffic, and optional licensing for SQL Server if it's applicable. And Google Cloud's pricing calculator will make it easy to estimate costs before launching your instance. All right. Couple of practice questions. Let's say you're using a single Cloud SQL instance to serve your application from a specific zone. You want to introduce high availability. What would you do? You would create a failover replica instance in the same region, but in a different zone. Creating a failover replica in a different zone within the same region ensures that the application remains available even if the primary zone experiences an outage. This is the recommended high availability configuration for Cloud SQL. Placing the replica in the same region maintains low latency while providing resilience against zone level failures. Okay, so let's go. We started the deployment. So we have to create the instance. We selected a MySQL instance. We can name it. We got the database version. Okay, we can do 1.00.1.1 instance ID. Numbers, all right. Oops. One. Version 1. Okay, and then we enter the password. Say admin, or you can generate here, or you can have it with no password. Okay, we have the region here. Multiple, single zone. You can specify your zones, primary and secondary. Then show the configuration options. You can select your machine configuration. This is going to be the instance type. All right. Number of vCPUs, gigabytes, and the cache available. Storage type, SSD, HDD, storage capacity, 10 gigabytes to 250, and enable storage increases. Connections, do you want a public IP to make this available using authorized network or private IP for internal Google based? And then you can add the network to your cloud instance. You can have backups enabled, how many days, for how many days, in what window, and then the days of the logs. You can prevent instance deletion, retain backups after. All right. So we covered that availability, we covered the machine type, and then maintenance window, week 2, so every other week. And then you can set the window day. All right. And the flags. All right. This is the granular aspects of the instance. Now this, oh, so you can customize how you would actually look at this instance and make any inquiries. All right. And then insights is likely go to cloud logs or query, goes to query insights. So within this, Enterprise Plus features, oops, client IP, storage store application tags, and then you'd set the labels. This would be good for your pricing calculator, and then create the instance. All right. And over here, you'll see cost estimated, I believe, per month. So, final questions or final thoughts. Cloud SQL is a relational workhorse of Google Cloud. It's a perfect choice when you want to manage PostgreSQL, MySQL, or SQL Server. You need backups, high availability, and IAM controls baked in. You want to focus on schema and data, not infrastructure. If it's in the web applications, BI tools, backend services, and internal dashboards. And thanks to built-in tools like Dataflow, BigQuery Federation, and runtime integrations, Cloud SQL plays well in every layer of the cloud stack. Now we're on the Cloud Table. Cloud Bigtable. Let's go here. Cloud Bigtable. This is a data solution designed for the largest workloads on Earth. Okay. This introduces Google's NoSQL database service built for scale, speed, and seamless integration with the rest of its big data ecosystem. Have you ever wondered how Google indexes the entire web or how YouTube keeps tracks of billions of videos, cloud storage, and cost optimization? This is how. All right, so what is Bigtable? Bigtable is a wide column NoSQL database. It doesn't use tables with joins or complex relationships like traditional regional databases. Instead, it's a key value store where each row is indexed by a single key. Each row can contain thousands of columns. Columns are grouped into column families for storage efficiency. The result, blazing fast reads and writes, even across petabyte scale datasets. The structure is perfect for Internet of Things sensor streams, time series metrics, real-time analytics, log data, financial transactions, or machine learning feature stores. So on the exam, remember that Bigtable is optimized for large, sparse datasets with predictable read-write patterns. Use it when high throughput and low latency are essential. So here's Google's DNA. Bigtable isn't just a product, it's a foundational part of Google itself. It powers core services like Google search indexing, Google Map and Earth, Gmail, and YouTube metadata. Its architecture inspired many modern big data systems, including Apache HBase and Cassandra. So a little bit of a deep dive. Each Bigtable instance is composed, let's try and create this, composed of nodes. These provide compute resources and handle requests. You can scale nodes horizontally as needed. Clusters. Clusters, each instance can have one or more clusters in different regions for geographic redundancy. And tables. Tables contain your row-keyed data and column families. And then a storage layer. This handles data durability, compression, and availability. Bigtable achieves low latency with automatic sharding, meaning your data is split and distributed behind the scenes without your intervention. It also offers performance at scale. Performance is what sets Bigtable apart. Every node can support up to 10,000 queries per second, millisecond level response times, massive ingests of export speeds, which is ideal for streaming analytics Python pipelines. And it's elastic, meaning you can add or remove nodes based on daily or seasonal workload. So when do you need to use Bigtable? You use it when you're processing sensor data from thousands of IoT devices, those Internet of Things. You're running real-time bidding engines. You need a time series backend for app usage metrics. You're training machine learning models and storing sparse feature vectors. And you want to analyze logs or click streams at massive scale. But Bigtable is not a replacement for a relational database like Cloud SQL or Spanner. If you need SQL joins, transactions, or multi-table consistency, use those tools instead. So here's a couple of practice questions. You want to optimize the performance of an accurate real-time weather charting application. The data comes from 50,000 sensors reading or sending 10 readings a second in the format of a timestamp and sensor reading. Where should you store the data? We chose Bigtable. Why? Because it's optimized for handling large-scale time series data, which fits the pattern of the sensor readings. It's ideal for real-time, low-latency access and analytics. With 50,000 sensors, each sending 10 readings per second, you need a database that can handle 500,000 writes per second and perform efficient time-based queries, making Bigtable the perfect fit. All right. So Bigtable shines even brighter when integrated with other GCP services, like Dataflow and Apache for stream processing, BigQuery via federated queries, AI platform for feature engineering, PubSub for ingesting real-time data, and cloud monitoring for visualizing performance and alerts. So here's something for the exam. You can know how Bigtable fits into an analytics pipeline. Usually, this is as the ingestion point, with data later exported to BigQuery or processed via Dataflow. A couple of things about security and reliability. Bigtable offers IAM-based access control, VPC service controls for data exfiltration protection, encryption at rest and in transit, and 99.999% availability with multi-region replication when configured. You can also enable audit logging to track who accessed what. This is crucial for compliance and monitoring. So let's start to create one. Just table. Got the instance ID. Okay, continue with the storage type, SSD. So you want to choose SSD for performance and HDD for cost. All right, so that latency and reads and writes. Remember that. We're just going to stick with this. We're not going to actually create this. Then we'll configure this with the cluster ID. We had that earlier, the region. Let's do US, Central Iowa. Yeah. Zone 1A. Or we might be able to do scaling, right? And then we can set up auto scaling so that it can scale up as needed to remove more nodes or add nodes as needed. And then, let's see, you have encryption options, Google Managed Encryption Key or the Cloud KMS, and a couple of advanced options for replication clusters. All right, we're going to cancel that. So to wrap up Bigtable, in summary, Bigtable is a NoSQL built for scale. It handles billions of rows, petabytes of data, and millisecond latency. It's tightly integrated with Google's big data stack and it's ideal for use cases where speed and throughput matter more than SQL functionality. All right. Next up is Cloud Fuse. Okay. Imagine you're in a scenario where you're working with an older application, maybe a legacy data processing tool or scientific workflow, and it expects to read from and write to a standard file path like data dash input or mount dot output. It's looking for a POSIX compliant file system, but you, the modern cloud architect, know that object storage like Google Cloud Storage is the way to go for scalability and cost efficiency. So how do you bridge the gap? Cloud Storage Fuse. What is Cloud Storage Fuse? It stands for File System and User Space. And it's a specialized open source adapter that lets you mount a cloud storage bucket as if it was a local disk. So with a single command, you can use you can use you can use GCS buckets into a mountain file system accessible to your VM or application, read and write using ordinary tools like copy, like CP, MV, LS, or even custom scripts that weren't designed with object storage in mind. All right. So give you a good one-liner: CF fuse GCS GCS fuse to your bucket. So my data bucket to mount my data. This would mount this here. So this is going to unlock an entire new set of workflows, all using your existing code base. All right. So use cases for Cloud Fuse include, while while it's not as performant as direct API calls, Cloud Storage Fuse is incredibly useful in certain scenarios, like scientific computing workflows where legacy tools write to mounted volumes, CI/CD pipelines that expect build artifacts on local paths, log aggregators that can scan a folder for new files, and command line tools and scripts written long before cloud native storage became the norm. If your app doesn't know about GSUtil, Bodo, or GCS APIs, Fuse is your translator. But know the trade-offs. Here's where the architect level thinking comes in. Cloud Storage Fuse is a convenience layer, not a performance engine. Compared to native object access through REST or GSUtil, Fuse introduces higher latency due to metadata polling and caching, eventual consistency, especially in the write-heavy directories, and no full POSIX compliance, like no hard links or file locking. So while Fuse is elegant for compatibility, it's not the right fit for high-throughput parallel writes, large-scale analytics ingests, or systems expecting real-time sync or file locks. So for the exam, use Cloud Storage Fuse when your application architecture or code dependency require file system semantics, but you still want to benefit from object storage scalability. Okay? So how it works is that behind the scenes, Fuse runs as a user space daemon. It will mount to your GCS bucket at a local mount point. It'll handle object to file translation in real time. It'll cache metadata and file contents, and it'll use your GCP credentials to authenticate, including service accounts and workload identities. So you can customize mount flags for cache control, read-only access, or parallelism. And yes, it works on Linux VMs, GKE nodes, or even your local development machine. All right. So here's a Cloud Fuse question. Let's say you're working in a highly secured environment where public internet access from the compute engine VMs is not allowed. You do not yet have a VPN connection to access an on-prem file server, but you need to install specific software on a compute engine instance. How should you install it? You should upload the installation files to cloud storage, configure the VM on a subnet with a private Google Access subnet, assign only an internal IP address to the VM, and download installation files to the VM using GSUtil. Why? Because when you're configuring the VM with a private Google Access subnet and downloading the installation files from the cloud storage, this ensures that you can securely access Google Cloud services without requiring a public IP address. And private Google Access allows VMs on a subnet to reach Google APIs and services even without external IP addresses. So it's ideal for secure environments. All right, so let's shift gears a little bit. Suppose you're planning a large data migration, maybe from Azure, AWS, or on-prem, right? Fuse isn't the best tool for that. Instead, Google recommends the Storage Transfer Service, which is for cloud-to-cloud transfers or recurring sync jobs. Transfer Appliance, when you're moving tens of terabytes physically, or the GSUtil-MCP for multi-thread parallel copying in shell scripts. The key threshold is 20 terabytes. At this point, transfer efficiency and error handling become critical. Specialized tools like parallelism, checkpointing, and resumable uploads. Because Fuse, and this is about the security in IAM, because Fuse mounts GCS buckets using your authenticated credentials, you retain all the fine-grained access controls you'd expect, like restricting access by bucket IAM policies, limiting write and deletion access via cloud identity, and enforcing encryption at rest and in transit. And since it's open source, you can audit or extend the Fuse behavior to suit specific organizational policies or workflows. So to wrap up, in the age of containerized event-driven applications, you might think local file systems are obsolete, but the truth is they're still everywhere. Cloud Storage Fuse offers seamless, low-friction bridge between legacy expectations and modern scalability, and it brings Google Cloud Storage into your workflows without forcing a full refactor, saving time, money, and developer sanity. As you design solutions for, or prepare for your exam, remember, Fuse is about compatibility, not performance. Use it for POSIX access, legacy tools, or quick bootstraps. Don't use it for high throughput, low latency needs. That's what the native GCS API is for. All right. Next up, Cloud Spanner. This is the most ambitious and trailblazing innovation in Google Cloud's uh, data platform. Let's see if we can pull this up. All right. Cloud Spanner. Now, imagine combining the rigor of a traditional SQL database with the limitless horizontal scale of NoSQL. Imagine not having to choose between ACID transactions and global availability. That's the magic of Cloud Spanner. It's built for modern global applications. See, Spanner is fully managed, globally distributed, and strongly consistent. It's a rare trio in the database world. It's built for mission-critical workloads. So Spanner isn't your average managed SQL database. It's specifically engineered for mission-critical systems that must never go down, always be consistent, and scale across regions or continents. Whether you're powering a global payment system, running a telecom backend, or managing live game sessions across time zone, Spanner is designed to be your single source of truth globally. So how it works. Pax and precision. At the heart of Cloud Spanner is Paxos-based consensus algorithm. It's a mechanism that ensures that every write is agreed upon by a majority of replicas before it's committed. This eliminates race conditions. It ensures that even in a globally distributed environment, you never have to worry about split brain data or right wins logic. And yes, that means true ACID compliance, even across regions. Spanner also uses TrueTime, which is Google's hybrid time API that leverages atomic clocks and GPS satellites to provide globally synchronized timestamps, a breakthrough that enables serializability at a global scale. So Cloud Spanner, for the exam, note this, that Cloud Spanner is unique among relational databases for offering strong consistency, horizontal scale, and multi-region writes in one solution. There's no replication lag, no eventual consistency compromises. So Spanner replica types are resilient by design. It doesn't just restore your data, it replicates it intelligently. Every Spanner instance is backed by multiple replicas, and they come in three types. Read-write replicas, these are the primary nodes where transactions occur. They handle both reads and writes and live in a specific region. Read-only replicas, these are distributed across additional regions to provide low-latency reads closer to end users. They sync from the read-write replica, but cannot write to the database. Then there's witness replicas. These don't store data, but participate in consensus voting. They add fault tolerance and help decide which writes get committed. Thanks to this structure, even if a data center fails, Spanner continues to function, routing around outages without sacrificing correctness. Performance and scalability. Each node can support up to 10,000 queries per second. That's per node. And nodes are horizontally scalable. Need more throughput? Just add more nodes. Spanner will rebalance and the data automatically. It supports sharded tables, index columns, SQL joins, and even foreign keys, all at massive scale. So let's create a scale instance. Okay. Choose the edition. Let's go for standard. You see the pricing, standard edition. Continue. We name it. Choose Spanner 2025 0401. Okay. And choose a configuration. Regional, dual regional, multi-regional. This is provision, so it's not going to give us that. Okay. We'll set it in Los Angeles, right? $13 per hour. And then, let's see, compute capacity. 4. You can see it set up by nodes or processing units. Okay. Enable default backup schedules, and then you can create. All right. And you can use standard SQL to create tables and then indexes and then foreign key constraints. All right. So you can interact with your Spanner instance using the Cloud Console, like we are. You can do client libraries or the Google Cloud CLI, all while relying on automatic backups, replication, and scaling behind the scenes. And there's built-in security and IAM integration. Spanner integrates with Cloud IAM for fine-grained access control, customer-managed encryption keys, audit logging and cloud logging, or audit logging via cloud logging, and optional private services if you want to keep your traffic off the public internet. It also supports identity federation so you can control access with existing identity providers like Okta or Active Directory. So when do you want to choose this? You choose this when you need strong consistency across global deployment. You want single functionality with NoSQL scale. You're replacing a sharded, self-managed PostgreSQL or MySQL fleet. You're designing for 5 nines uptime and automated failover. That's 99.999%. But if you only need a few hundred gigabytes of data and a regional database will do, Cloud SQL is more cost effective. For the exam, use Spanner for workloads that must be globally available, horizontally scalable, and transactionally consistent. Always justify the cost with architectural need. So here's a practice question. You're tasked with building an online analytical processing, OLAP marketing analytics, and reporting tool. This requires a relational database that can operate on hundreds of terabytes of data. What's the Google recommended tool for such an application? That would be Cloud Firestore because it offers real-time synchronization across devices. BigQuery is designed for large-scale data processing, is highly optimized for OLAP workloads, and it can handle hundreds of terabytes of data efficiently, making it an ideal solution for marketing and analytics reporting. While Cloud Spanner is powerful, it's more suited for OLTP. Oh, sorry. The answer was BigQuery. Sorry about that. Because BigQuery is designed for large-scale processing of tabular data. Why? Because BigQuery is designed for large-scale data processing and highly optimized for OLAP workloads. It can handle hundreds of terabytes of data efficiently, making it the ideal solution for marketing analytics and support and reporting. Other tools like Cloud Spanner are powerful, but more suited for OLTP workloads. Cloud SQL has size limitations. Firestore would be designed for transactional document data, so not analytics at this scale. So, final thoughts are that while Spanner represents Google's deepest expertise in distributed file system, it's what happens when teams behind Bigtable, Megastore, and TrueTime get together and invent relational databases for the global cloud era. If you're building for users in multiple continents and want guaranteed correctness and can't afford to go down, Spanner is your option. All right. That concludes chapter 3. The next chapter is going to be networking in the cloud. Thank you for joining me.